When you type a prompt into a modern AI and watch it instantly draft an essay or solve a complex math problem, it is easy to feel like you are communicating with a digital sorcerer, but that illusion quickly shatters. This creates a gap between our expectations and the machine's reality. When we provide a brief, ambiguous prompt, the system has to fill in the missing details with the most common statistical averages from its training data, which is why AI responses often feel generic or factually untethered. If we pull back the curtain on this interface, we find there is no thinking mind inside. There is no reasoning, it has no memory, and no actual comprehension. Beneath the hood is a mathematical machine. During its training, it essentially absorbed a lossy compression of the internet. Billions of human sentences scraped, mathematically compressed, and stored as numerical weights. The machine has one mechanical goal. It does not think, it calculates. Given the words you type in, it runs an equation to predict the single most mathematically probable word that should come next. To exert control over these tools, we have to let go of the magical illusion. We need to look at exactly how this machine calculates those probabilities. A few years ago, early neural networks processed language much like a slow human reader. They looked at text strictly sequentially, reading one word at a time from left to right. This created a severe memory bottleneck. Because they processed sequentially with a very narrow view, these models would mathematically lose track of the beginning of a long sentence by the time they reached the end. In 2017, the Attention is All You Need paper introduced the transformer architecture. This design replaced sequential reading with a method for seeing an entire block of text at once, effectively removing the memory bottleneck. The first step of this modern process is called tokenization. Neural networks cannot process letters, they only run on numbers. So text is sliced apart into chunks, each assigned a unique numerical ID, called a token. Often, these tokens aren't whole words. Outside might split into subword segments like out and side. This granular vocabulary allows the machine to recognize millions of combinations efficiently. Tokenization creates the numerical alphabet, but the transformer's core innovation was the ability to evaluate every one of these numbers simultaneously. It does this through a mechanism called self-attention. Instead of reading word by word, self-attention allows the AI to look at your entire sequence of tokens all at once. The machine draws mathematical connections between every single token in your prompt. It assigns a numerical weight to these connections based on how much the words matter to one another. For example, if you write plant, it calculates the statistical weight of surrounding words to pin down the exact numerical definition of that target token. Once that entire web of context is weighed, the machine does one thing. It calculates the highest probability next token, adds it to the sequence, and restarts the entire calculation. This is called the auto-regressive loop. The AI is not understanding the concepts you type. It is mapping the statistical gravity between words to guess the next logical piece of the pattern. Because the AI doesn't have a mind to read yours, we have to approach it differently. The quality of the output it generates is dictated by the quality of the context you provide it. You have to treat it like a calculation. You must feed the machine's strict boundaries to intentionally restrict and guide its probability math. The first step of a strong prompt is to define the role. By telling the AI to act as an expert economist or a senior software engineer, you force the machine to pull statistical patterns from that specific area of expertise. Next, define the audience. If you specify that the output is for a fifth grader versus a board of directors, the machine automatically adjusts the probabilities of the vocabulary and tone it will select. Finally, set explicit boundaries. By telling the AI exactly what to exclude or restricting the length, you cut off unwanted statistical tangents and keep the mathematical loop focused on your goal. Understanding these contextual parameters changes your relationship with the interface. You stop interacting with a mystery and start operating a precise machine, pulling the levers that guide its mathematical predictions.